everybody. My name is Adam Penna, and I'm here to continue the conversation in 3D printing and additive manufacturing. And today I'm happy to have with me, coming all the way from Munich, Germany, Lin Kayser, who is joining us from Hyperganic. And Lin, welcome today. Wonderful to have you here.
Thanks, Adam. Yeah, thanks for having me.
Yeah, wow. So I know, like I said, you're in beautiful Munich, Germany, and wow, it's a wonderful place to visit. I've been over there a bunch of times and look forward to visiting again because of all the beauty there. There's so much artistic value inside of what's in Munich and all the beautiful buildings and the art and the design that went into doing that. And so I think it's a big hub for just that kind of thinking, you know, the artistic thinking, and also drawing that into the engineering world like we're doing now. There's a lot of great stuff happening in Munich. So it's lovely to touch base and to hear a little bit about things that have been going for you, because I know you've been working with Hyperganic as a CEO now for the last 5 years. So you're developing a software that is, you know, has a generative design embedded inside of it, but is looking at, you know, AI, artificial intelligence, and how to incorporate the two. So I'm very excited to talk to you about this and learn about what you've been doing with it, because it's a really hot topic right now. So how have things been going for you recently, and what had you develop over the last 5 years to get to where you are now?
Maybe a bit about how we actually ended up, or I ended up doing what I'm doing now, right? So, you know, I have an interesting family background because my father was actually an artist, you know. So, I mean, it's funny that you talked about Munich as like an artistic place, you know, because most people think, yeah, BMW and engineering. Yeah, and I mean, there's a lot of other things here going on. You know? So my dad was an artist, but awesome. So of course I have a lot of his artistic genes. But on the other hand, my uncle started the first private space company. So he was kind of the Elon Musk of the 1970s, launching rockets in Africa. So, you know, I have kind of both sides. And I think maybe with Hyperganic, I'm trying to combine both types of genes in my DNA, you know, to the ultimate engineering challenge. Now, you know, I got into additive manufacturing when I bought my first 3D printer in 2012. I had, you know, just recently sold my last company to a big US company, to Adobe. Awesome. I did something completely different. I did image processing for Hollywood.
Okay.
And I was kind of looking for the next thing. You know, I was diving into engineering because I always loved actually building hardware, you know, physical things. But I'm actually a software guy. You know, I learned how to code when I was 8 years old. You know, that was 40 years ago now. So computers look very different.
Yeah.
But I actually love physical things. And when I bought a 3D printer in 2012, you know, it was a revelation to me because it was kind of the manifestation of software in the physical world. You can think of something, you can code it, and now all of a sudden you can print it. And I was hooked. And, you know, at first I thought, well, it's a nice hobby and, you know, it's kind of interesting. And, you know, after a while I thought maybe I should be doing something there as my next project. But I couldn't really point my finger to it. And then I finally found it, you know. I mean, there's one thing that I got really frustrated about, you know, all my life. So I told you that, you know, in the 1970s, my uncle was starting to launch rockets. And I always thought, you know, by the time I grow up, you know, we would be flying into space. And we didn't, you know, somehow. I mean, of course, we're flying into space, but, you know, I mean, the space shuttle and these kinds of things, they were kind of boring compared to what I thought would happen. And, you know, the future happened much slower than I thought it would happen, you know. So I started to ask myself why. And the answer is innovation is just incredibly hard and incredibly slow, especially in physical products. And, you know, I was kind of thinking, you know, yeah, of course, you know, maybe it's just nonsense, you know. This is just the pace at which innovation happens, and there's nothing you can do about it. But then I realized, wait a second, I just realized, I just witnessed for the last decades, a revolution in innovation that was incredibly fast, and that was in PC technology. So, you know, when I started out programming, you know, PCs were really clunky and really simple. And, if you look back the last couple of years, just what happened in computer technology and smartphone technology and these kinds of things, I mean, it's still incredibly fast. 10 years ago, we didn't have smartphones. 20 years ago, almost nobody used the internet. 30 years ago, almost nobody had a PC. 40 years ago, all of this stuff didn't exist at all, right?
Yeah.
So incredibly fast. Now look at almost any other physical object, it hasn't really changed that much. Look at a car, except for Elon's cars, which I'm a huge fan of.
Yes,
but if you strip away all the plastic parts of a modern semi-modern car from a German manufacturer, it looks like a car from the 1990s. So not really that much innovation in the last 30 years. So why is that? And that's a question I started asking myself. And the next question I started asking myself, and that brings both of it together, is could additive manufacturing really be the thing that brings the speed of software, of Moore's law, into the innovation of physical objects? And this is when I got really hooked, and that is, basically the founding idea of Hyperganic, building a software ecosystem for additive manufacturing that dramatically accelerates innovation in physical objects.
Yeah, that's exciting. I mean, that's really where we're looking at, and we're talking about, how nature plays into that design. Nature builds certain ways for a reason, and it sets things up a certain way. And to look at that inside of a building mechanical structure, inside of what is going out there in the world today, we see a lot of that starting to change. It's kind of reaching that tipping point of people looking at that as a design concept, that generative design setup. So everything that Hyperganic's been doing, I've seen, a lot of other softwares out there kind of hinging on the same sort of thing. So what advantages does Hyperganic have over existing softwares out there?
Well, I don't think there's anything comparable out there at this point. We thought how to do design fundamentally. So there's a lot of tools out there that do generative design, and a lot of them are basically, they take an existing object and they fill it with some kind of weird structure or whatever. And then, you have a topology optimization or something like that. What we are doing is we are taking the software paradigm where you build functionality, that's very adaptable, and move it to the physical world. So what we are not doing is we're taking an existing object and then, we remove all the material that we don't want. What we do is we build stuff from scratch. And you mentioned nature. So this is our big role model in a way. Because nature is the ultimate engineer. Everything that nature builds are incredibly optimized, and not an atom too much, at the right spot. A tree, if you look at a tree outside, it's the perfect object for that specific location. It uses the absolute minimum amount of energy. It uses the absolute minimum amount of material, and it's perfect. I mean, it fulfills its function perfectly. So what if we could engineer objects like that? So that was the original idea. Now, how do you actually build these objects? And now there's a fundamental flaw in the way we currently design physical objects. And the fundamental flaw is that we are using the same methodology that we used for for engineering in traditional manufacturing. In traditional manufacturing, you start with a big block of material and then you remove everything that you don't want. Right. So the object that you're building is comparatively simple. Now in nature, you grow things, basically placing atoms in place. And a human will actually never be able to create an object like that in the current paradigm. What's the current paradigm? The current paradigm is basically the same paradigm that the old Romans used and that Leonardo da Vinci used, and that we're still doing, is basically we draw an object on paper, or now today we draw it in a computer. So it's a laborious and labor-intensive process that depends on the amount of time that an engineer is willing to invest in the design. So the more complex and the more functionality you want there, the more time you have to invest. And yes, there are some ways to get around that and to help yourself. And some of the tools that you mentioned help with that a little bit. but it's still, it's like one engineer sitting in front of a computer, drawing the thing and creating it. And it's the imagination of the engineer. So what you have in your head, you're putting on screen.
Mm-hmm.
Now, this is not how nature works. There's not like some guy sitting on a cloud, designing the next tree. It's evolution, right?
Sure.
So how can we move that into engineering and manufacturing? And so we started with a really simple idea. Let's move atoms in place in space. So instead of building an abstract thing that is defined by the surfaces, let's really move all the individual atoms in exactly the right place. And so we started with a completely new geometry kernel that's fundamentally built on that idea, that you move tiny particles in space. And coincidentally, that's exactly what a 3D printer does. It moves tiny particles in space. But there's no software but ours right now out there that can actually model everything that a 3D printer can print. Why? Because fundamentally you could fill the entire build volume with just random atoms, and that would actually be your engineering model. Now, how can you do that with a traditional software? There's no way. It's way too complex. But we can do that because we built a new geometry kernel from the ground up that's built on voxels, high resolution pixels, three-dimensional pixels at the resolution of the printer or higher. That allows us to model anything that a printer can fundamentally and theoretically actually build. Now that's the foundation. And that took us a couple of years, because that's really hard to do. It's not hard to do voxels, it's hard to do voxels that perform at a performance that is acceptable, right? Fortunately, we don't have to move atoms. We can move the little particles of powder or whatever that the printer outputs, but still, it's a lot of work. And then the next step is, it's nice to have something like that on screen, and it's nice to model fantastic things on screen, like the rocket engine here that we modeled.
Beautiful picture there.
It's much nicer to actually build it in real.
Yeah, there you go, on the build plate still. That's beautiful, yeah.
Exactly. Wow. So how do you get from the screen to the printer and to the output? And that took us also a little while, so we started working with 3D printer manufacturers very early to find a way to output to their individual printers. And so we did all the printers. We can output to anything from powder bed systems to SLA resin-based systems to G-code for extrusion-based systems. Perfect. And now we had a technology stack that allowed us to, in theory, model anything and output it on any printer that we wanted to. And now comes the fun part. How do you do engineering in this new world? In this new world, you don't do engineering by sitting in front of a screen and drawing something. We could do that as well. You could draw voxels, but it's not so much fun because there's lots of voxels that you have to set. Now comes the software part where you say, I define an algorithm, I define a module that creates objects of a certain type. And what you see here, this rocket combustion chamber that we did, this is 3 years ago already, we did that. It's an object that was defined completely by algorithms. There was no human drawing anything there. There was fundamentally no basic geometry. It was all created from scratch using algorithms. And so whenever you see a hyperganic object like that one, it's not one object. It is basically one object of many, many, many that could be defined by the same algorithm. And this is really the fundamental game changer, where you don't design one object, you design a way to create objects. So instead of creating one blueprint, you create an algorithm that creates many blueprints. And this blueprint is adapted to exactly the use case that you want. And this is really, really interesting because it allows you to do many, many different things. First of all, there's 3 sweet spots for our technology. One is incredibly complex objects, because as I said, we can address every particle that the printer can output. So if you need a heat sink that looks a little bit different than the stuff that you usually do.
Wow. Yeah. Now that is beautiful. That is the epitome of generative design. That is gorgeous.
Exactly.
Yeah.
So,
Wow.
I mean, we started out with the idea, you know, how can we maximize
So
the surface
material
area?
here is what?
Copper.
Yeah, that's what I
Copper.
thought. It's a yeah, heat sink. That's amazing. Look at
Yeah.
that. So the heat, that, like when you're talking about that, so people know, you have to have surface, and the most surface you have there, you could dissipate heat. So you're looking to work inside of small spaces and add as much surface. And when you're talking about nature, nature does that best. So to be able to capitalize that and bring it into a software like you're doing and print something like that, I could stare at that all day. That is amazing. That's beautiful. Thanks for sharing that, Lin.
Also a great brush.
Yeah. Yeah. It's got multi uses. Yeah. Why
No,
not?
I mean, the fun thing is, I mean, so we maximize the surface area, so you end up with something that looks a little bit like coral or something like that.
Yeah.
Right? But then we also optimize the aerodynamic, funneling of the air to the bottom of the heatsink, because of course, otherwise, you know, you will just have like a, you know, a cushion of air that flows above it, you know. But if you funnel it in, well, there you get a real, step ahead.
Yeah. Purpose.
In terms of the heat exchange, right? So incredibly complex objects. This is one of our sweet spots. I mean, we work with people who do filter systems with nano printers and heat sinks, you know, heat exchangers in general. You know, there's lots of really cool stuff there. So this is a real sweet spot. But the other thing is, of course, once you have algorithmic design, you can automatically create objects. So where do you need that? Well, in the medical field, for example,
Yes.
right? Because you don't want the prosthetics of somebody else. You know, you want your leg. You know, we were working with a company. Yeah, for example, here's a Munich company. They print skull replacement caps out of PEEK, you know, a high temperature polymer.
Mm-hmm.
And of course, you know, you want it to fit. So, you know, it helps you if you have an algorithm that creates something that's fundamentally always fitting, you know, the right person. But of course, there are other things like consumer goods. You know, here we have a helmet, for example, a bicycle helmet.
Yes.
And that was derived from a human head, right? You know, we scanned a triathlete's head, and you know, her head is now perfectly fitting. I don't know. Do you have a cycling helmet that fits?
Yeah, they're all a little bit loose in one way or another.
Yeah, well, I don't think anybody has one that fits. I have 5 kids. You know, can you imagine buying new bicycle helmets every year? That's such a fun task. So, you know, it takes 3 days or something, and then, you know, everybody's kind of unhappy because it doesn't really, you know, fit. Now, a helmet should be created for your head and not for some generic head, because everybody's head is different. But there's another thing. As people fall, you know, statistics are generated, you know, how people actually fall. And, you know, couldn't we actually take these kinds of pieces of data into account when we design the next helmet? So what we did here is we used statistical crash data, you know. So if you look at the top, you see that, you know, it's very, you know, there's a lot of transparency to air.
Yeah.
But if you look to the sides, you know, it's actually pretty solid. You know, why? Well, nobody falls like that. You know, people always fall like that and hit their heads like that.
Yes.
So make it strong here, add ventilation here. You know, makes a lot of sense.
Sure does.
So, you know, and if people send back their helmets after they've fallen, you know, the company could actually take into account crash patterns and stuff like that. And it could go directly into the manufacturing of the next helmet. So this is the power of mass customization. I mean, first of all, it fits the right person. And secondly, you can take new information into account, you know, fatigue, stuff like that. And the next production run immediately has a better product. So this only can happen if you have algorithms creating these kinds of things, because no human ever has the time to adapt everything all of the time. I mean, imagine a human-driven workflow for customized helmets. I mean, each helmet would cost like $2,000 or something like that, because somebody would have to design it, you know, interactively. So if you have an algorithm, it can do it automatically. But then there's the third area. So I said complexity is a sweet spot for us. custom design is a sweet spot for us, and there's lots of stuff out there that needs to be custom designed.
Yep.
And then the third part is when you have algorithms creating objects, you can optimize objects. So I can do what we did with the rocket engine. Instead of creating one rocket engine, we created thousands of rocket engines and evaluated them, in a simulation, how well they performed. And then over time, you find the perfect one, and then you produce that one, as much as you want.
That's what I was going to ask about, because obviously you're talking about, multiple options, and, we call that iterations. You're able to look at multiple ways of doing the same thing. And to be able to then analyze that afterwards, I was like, okay, you get all these objects, but then how do you, derive the one that you're going to use, or the best one? And of course, running it through simulations and being able to do that. But to quickly do that is always the the challenge, because if you have so many options, you have to run so many simulations, but you kind of know what you're doing dependent upon the actual case scenario, what application it is. And that's where it actually gets. I know the AI is doing a lot of the work, but you also have the human interface where you have to set all this up. Is that correct? That's part of it, setting all the algorithms and things like that. Is that always different per case, per application, setting up those algorithms inside of your environment, that type of thing?
Well, I mean, it's like all software development, once you get it, when you get started, you have to do a lot of work.
Right.
Once you're a little bit further along, you can use existing modules. And of course, fortunately, our customers can use existing modules that we've created, that maybe they've created in-house. But yes, I mean, it is, of course, unfortunately, not a magic box, where you just throw in your ideas and then it comes out.
Come on,
rocket
man.
engine. Yeah, we're working on that. We're not quite there yet. At some point, I think it will actually resemble something like that. But it is an effort. And you mentioned AI.
Yeah.
And so what is AI? I mean, there's AI, if you look through, the decades that people talked about AI, when I was a little bit younger, AI was expert systems. Today, AI is deep learning, reinforcement learning, these kinds of things. The first type of AI that we do resembles expert systems. It's a lot of if, then, else. If the pressure is so and so much, then do the cooling channel in a certain way. If the interface is so and so, then adapt to it in a certain way. So today you wouldn't call that AI anymore. You would call it an expert system or an algorithm. And that's what we're doing. Now, AI has a very, very interesting role in what you just pointed out. Simulation is slow. Mm-hmm. Now, there's a lot of efforts to make simulation faster. I mean, there's like these crazy microchips now that have 1 million cores on it, etc., that are specifically designed for these kinds of things, but they're not generally accessible. So how can you speed up simulation? Well, how do we human engineers actually speed up these things? I mean, we're not designing something random and then running it through simulation and hope it will work. I mean, we have some smartness about it. We know that a car with rectangular wheels is probably not going to be a great car.
Yeah, we've tried that before.
Designing it. So we tried that before and it didn't really work. We are not doing it again. Yeah, we have some kind of intuition. We know, okay, this stuff is better. This is not so good. And sometimes, it's actually bad that we have that intuition, because it kind of distracts us maybe from a much better solution out there. But very often our intuition is actually right. I know that, if I hold something here and I let it go, then it will probably fall down. So I didn't study the laws of physics, and I'm doing like a differential equation while I'm looking at this object. I just know from experience, because as a little baby, I let drop a couple of things 1 million times, and I realized, okay, my brain now knows if I let go of it, it falls down. So we can do stuff like that to hypercharge simulation. So we can try to predict the result of simulation and feed it back into a neural net, and create reinforcement learning that way. And that means I don't have to try out everything. So I build a machine intuition in a way. And that machine intuition tells me and guides me, what part of the solution space I should actually look at and what part I can just discard because, probably will not amount to anything. And that is one way you can speed up, this fitness function and the simulation, because, well, if we try to emulate nature perfectly, we have to throw around atoms for 4 billion years and then hope that something interesting comes out of it. So we usually don't have that much time. So what we usually do is you start with things that already work. A circular wheel is probably a good idea. A piston probably is roughly this size, etc. So you don't start completely from scratch, right. But you have to give the system enough degrees of freedom so it can come up with something novel. And this is what we've done here, right? Yes, of course. A rocket engine probably is circular. The first ones we tried weren't circular, so we very quickly added that constraint. There's certain general geometries for cooling channels that probably make sense. So you're not just trying to do random stuff. You're experimenting with maybe 20 different fundamentally building blocks of geometry. So it's a little bit like working with Lego, right? So you could build a space station out of clay, but it's much easier to build it out of Lego because you have some constraints about what you can do. But of course, you cannot do everything. And this is where you have to be careful with the constraints. But the fundamental result is that you have these algorithmic Lego blocks that allow you to build really, really complex objects relatively quickly. And usually you end up with surprising results. And this is, to my knowledge, the first software ecosystem that was fundamentally built from the ground up for this type of engineering. And that's what we've been busy doing the last 5 years.
Yeah, it makes sense. And I know you touched a little bit on a few things there, of course, talking about the artificial intelligence that goes into Hyperganic. And then you were kind of getting into how you set up for an application. Is that the modules you're talking about? Can you better define what the modules were? Was that what you were referring to when you actually set something up for, say, the actual combustion chamber, and then you have a certain module that fits rocket engines? I mean, what does the module actually look like?
Well, I mean, a lot of them are just modules that create geometry. I mean, we have a software module that creates these kinds of structures. Now, The interesting thing is, it's great for maximizing surface area for heat exchangers. But one of the things that we found is because it's fundamentally a tree-like structure, it's actually very stable. So people have been, my engineers in the back office here, have a separate building full of people that just create crazy objects.
Yeah.
They shoehorned this into, other products that didn't need big surface area, that just needed to be light and that needed some stability. And so, it's sometimes surprising what you can do with the same algorithm. It wasn't designed for that, but you can use it for something else. And I think what you are ending up with is something that happens all of the time in software development. I mean, you create a database and maybe you have one specific use case in mind. Then somebody else comes along and says, wait a second, I can use that for a completely different application, because if I generalize it a little bit more, then I can use it for anything. And this is happening now with geometry. And that's the fun part of it. And this is really the validation of the original idea that we had, is that the 3D printer is basically a universal output device. And if we can feed it with algorithms, we can build almost anything, but we can also speed up the creation of these things, because software is so incredibly flexible that it allows us to do a lot of things much quicker than if you have to re-engineer, and you're limited by the imagination of the engineer, and you're limited by the working hours of the engineer. Sure. So engineers in the future, honestly, engineers are, it's actually a sad thing. Engineers have been used to do manual labor to a certain extent. Drawing their ideas on screen. Wouldn't it be much more fun for an engineer to come up with the question and not so much come up with the answer? So
Yeah.
ask a really, really precise question and then let the computer actually do the stupid work.
Mm,
And so this is really, personally, this is my vision, that we define things in very abstract terms, and then software modules come up with really, really sometimes surprising answers to these problems. And this helps us jumpstart innovation in physical products. And I think it's way overdue, because a lot of the challenges that we have in the world today, things like global warming and all these things,
sure.
they require engineering solutions. So if we engineer things in this slow and really complicated way that we've been doing it for the last, I don't know, 2,000-3,000 years,
Sure.
then we're probably not going to out-engineer these problems. I think what we need to do is what happened in software and hardware in the computer industry, is that we really create radical change relatively quickly.
Mm. Yeah, I think right now that's happening too. I think it's a software revolution out there. There's so many things that are happening inside of, the technology has gotten to a certain place. The machines have been out there for, 30 years. And now there's the way that the softwares are kind of evolving to interact with the machines. And I see that on all sides. So what Hyperganic is doing is amazing, but it is, and I like that it's you say we empower visionaries. And this is a visionary way of looking at design. It's a way of empowering the AI to do like you were saying, doing the hard work for you, going out there and looking at your design constraints and actually coming up with a solution in multiple iterations, and then being able to kind of, look at what you need to use for your specific ecosystem, what's happening in the front. And they, from design to being out there in the industry, there's a whole ecosystem of what has to happen, how the manufacturing facility is actually going to come up with the part, what's going to go on afterwards. So there's a lot to look at. And it's not just that one function of, hey, how many iterations we could spit out, but it's how many that are going to work for all sides, coming, from cradle to grave inside of the design process and the manufacturing process. So
yeah, absolutely. I think the big challenge now is to change the mindset of the engineers and the people who are actually creating these kinds of objects, the companies. So you basically read off our website, we empower visionaries.
yeah.
Now, one of the things that I found is that there's not that many visionaries out there. So, how can we actually help people understand, what is possible now? And so I created a team. It's called Advanced Projects, which is funny because the director always says, it's so funny because every project that we do at Hyperganic is advanced. So I'm running everything. So, but what we created is a team that just shows people, what is possible. And that has actually helped move these conversations to a much higher level. It's very hard to go to somebody and say, hey, we can create something completely amazing. And then they still kind of think along the ways of their traditional engineering. You have to show people, you have to put it in front of them. If you take, I don't know, take a heat exchanger, where you have like a completely crazy geometry,
Yeah.
it has grown. You have to show it to people and put it in front of their desks and say, do you want that? Do you want to work on this, or should I go across the street to the other guy?
Right. No, you have to show people. And I think that's a big part of this whole process, as I've seen in a lot of these conversations. It comes down to what you're talking about. It's security, right? People need to feel secure on what's happening. But what is that? What is the security? Where does it come from? Education. You have to be educated on how things work. You have to spend the time to sit with a team or an engineer and work through what they're doing, understand where they're coming from, and then feel comfortable enough to go through and work through a project with you. That's a security thing, and that's an education. So those two topics keep coming up in all this, is a security and education, and that kind of starts pushing things forward. But if a company isn't open enough to sitting and working with people and just wants to force something on someone, that's where things don't happen. It's having the open mind to work together and to think outside of the box or outside of the voxel and start to get into what's really going on, what's really needed here, what are we trying to achieve together, and how we could do that. I like when people work inside of those partnerships to open up their mind, to open up the whole process of manufacturing, to see what can be done that's not being done today. And that's what gets me excited. It's improving our lives now in many ways, you know, medical, aerospace, there's so many things that are happening that improve our lives. And 3D printing, additive manufacturing, the software inside of what's happening right now, it's just blowing my mind, because it really is taking that to the next level. So kudos, I think it's awesome. Yeah.
No, AM has been around for 30 years, as you said, but it has never been really used that properly. People use it for prototyping mostly.
Right.
Now we're at the point, because of the hardware that's there, the printers are there, we can now tilt entire industries to digital manufacturing based on additive and generative algorithmic AI-based design. And that's what we are driving forward. Unfortunately, there were enough visionaries so far to work with, you know, in the past couple of years. So we work all over the world, you know, in the United States, in Asia, and Europe. And there's lots of really exciting projects out there, but we need more. And so we're really looking forward to pushing the platform, you know, into many, many use cases. And hopefully a lot of people will adopt it, because, you know, fundamentally, I think the future of innovation depends on this. You know, we've, you know, out-innovated most of the production processes that we have today. Now we need to move to the next level. And additive is at the center of that. Not only additive, but additive is at the center of it. Additive plus algorithmic design, AI-based design, it's gonna change how the world will look like in the next couple of years. Because almost anything that you look at in your home, you know, outside, in the street, whatever, could be improved by these kinds of manufacturing technologies and design technologies. And so it's going to be a lot of fun, you know, watching how this will evolve over the next couple of years. And we are hopefully in the driver's seat. You know, we are absolutely going to push this forward like crazy.
Yeah, I was wondering, you're saying that. I mean, now that things are moving along and could understand so much about where you are today, what are some of the future plans for Hyperganic? You have some things you can kind of give us a peek behind the scenes of what might be coming up?
Yeah, I mean, we are, of course, I mean, so far we've been mostly in stealth mode. And, you know, hopefully by the time you see this video cast, a lot of, we are going to show a lot more than we are currently showing. But, you know, the big push for us is that we are going to open up the platform for a lot of additional people, for basically everyone, to work on the platform. We have a lot of really exciting use cases that we've been secretly working on over the last 2 years that I can't share right now. But our goal is to literally tilt an entire industry towards additive manufacturing and generative design. And, you know, this is a lot of our commercial focus right now, that we don't do like one little application here and one little application there, that we focus on a certain vertical that we've identified and push it so that it completely goes down the road of additive. And there's a lot of really, really exciting markets that are very large and that have been waiting for this. And fortunately now it's the technology that's ready, it's the hardware that's ready, and it's also the economics that now all of a sudden makes sense, because there's several things that need to play into each. I mean, as engineers, we only look at, is the printer ready, is the software ready? But is the question, is the material affordable? Is the printer ready to do actual mass production? Or is it boutique style manufacturing where somebody has to place something manually? So fortunately, I mean, if you went to last year's Formnext, you know, when you could still be physically present, you could see that every manufacturer was looking into automation. You know, can I put a robot in there that moves stuff out and stuff? Because I mean, in a factory, you don't have people running around with vacuum cleaners and, you know, moving build volumes around. you needed to have it fully automated. So this is happening. So the hardware is there, the materials are there, the software is coming along, and now the business case for the entire manufacturing chain makes sense for a lot of products. And these are the products that we are currently focusing on the commercial side. I can say publicly today that we're going to open up our platform for lots of third-party developers. And this is going to be exciting because, the moment you open it up to other people, they come up with crazy new ideas. They can monetize their crazy ideas.
Yep.
It's going to be a lot of fun. Yeah. And this is really what we've been working with for the last 5 years. So it's going to be a fun ride. Really looking forward to it.
Yeah, that's awesome, Lin. I know, people could check this out. It's hyperganic.com. Is that correct? That's where the website. So if you want to look into that more there. And so now we're looking at 2021, and it should be a great year. A lot of stuff that'll start to come out because, everyone I see over this last year has been challenging for everyone. Obviously, we've all had our own individual challenges, but the one beautiful thing I think I've seen over and over again is more people talking, more people opening up and talking together and looking at how we could do things together. And I think that's really beautiful. So I'm very excited to see what comes out of that with Hyperganic. And what you're talking about is opening it up to everyone to actually work on things. So again, being open, being able to be nimble and kind of change in this environment and really work together to make the world a better place. It's a beautiful thing. And thanks for being here today, Lin.
Yeah, thank you so much for having me. And this is really, a passion project for me. Yeah. And so I'm really looking forward to sharing what we've been building over the last couple of years.
Yeah. Well, Lin Kayser from Hyperganic, thank you for being here today.
Yeah, thank you. Bye-bye.